So last time we talked about how to use LU decomposition to solve AX equal to B. Okay, so we did this. Now we want to know what to do if there are some permutation involved. So this was for the case where there were no permutations. In case there is a permutation, what happens? Well, you have to exchange some rows. After you have done exchange of the rows, then LU decomposition still happens. So you have some matrix A, you shuffle some of the rows. The record of all the shuffling that you need to do can be kept in one single matrix. We call it permutation matrix P. So this is a long list of shuffles you have done, all of it compressed into a single matrix. Then P times A is a matrix that can be written as L times U. Okay, subject to proper shuffling, P times A can be written as L times U. The question now we want to solve is, what if we were facing a system that needed permutation, and how do we go ahead and solve that kind of equation in that case? So the question is, solve AX equal to B using this type of decomposition. So as an example, I pick a short one. Let's take problem 33 from page 70. This is on, we are still in section 1.5. So it says there is some matrix A that the book insists that you don't try to find it. So don't try to subvert the problem. Try to do it some other way. Say there is some matrix A that after you do some shuffling, and the book tells you what shuffling you need to do. Here it's a very simple shuffling. You just exchange the two rows of it. After you shuffle the two rows, it has a LU decomposition, and its LU decomposition is given to you 1, 2, 2, -1, 0, -3. So we are given this information. What we are asked is solve AX equal to B for right hand side B, which is also given 22, 8. Without finding A. So I wrote that in red. Let's see if we get that idea across. And let me emphasize, the language is clear what you're supposed to do. Just like that last problem on the first page of your exam that was asking you to solve such and such system by graphing, and just about everybody did it by algebra and tried to sell it as a graphing solution. So here is the same thing. So don't find A. I know you can go find A. I know you can go and do it some other way that you did back in the 8th grade or something. We don't want to do that. We want to know what is the role of the permutation. So we come and do the following. Say, okay, you want to solve AX equal to B. And the objective is that we want to use our permutation decomposition. Say, okay, let's bring permutation P in the picture. Who's P? P is this matrix that is given here. This is P. This is a permutation you're supposed to do. So take the two sides of the equation, multiply it by P. Okay, what do we get out of it? What we get out of it is P times A. What is P times A? It is this L times U. Okay, so this can be substituted by already made lower and upper triangular matrix L and U. P times B. What is P times B? Well, let's just go ahead and do this in our head. What is P times B? P is this permutation. When you apply it to this matrix, what does it do for you? What happens? Just, this is a record of swapping the two rows, is that right? So when you apply to B, it just flips it over. That typically referred to as B prime. So the right hand side, make sure you realize that the right hand side has to undergo same flipping. Okay, now we have LU times X equal to B prime. This is given, this is given, this we just found. These are given items. This is almost given, we just got it quickly. What we want to do is to find this one. So L and U, here's the L and U. B prime, this is B prime. How did we say we handle this thing? We say, okay, LU times unknown vector X is supposed to be my modified right-hand side. I go ahead and rename this portion, call it Y. Now I have L times Y is equal to B prime. The strategy is to go ahead, handle this one first, and find Y. Next, come back and say, who is Y? Y was U times X. So by then, you know what Y is. You can go ahead and approach this equation, and you know what Y is. You can go and find what X is. So let's just go ahead piece by piece. Who was L? This is my L. So I have L, which is 1, 0, 2, 1, times some unknown vector. Let's call it vector Y. So here's the first component of it, here's the second component of it, is equal to B prime, modified right-hand side. Modified right-hand side is 822. We said last time these kind of equations are very easy to solve because much of it is already done for us. Let's go ahead and write it in traditional format, see what does it look like. This is Y1 and no Y2s is equal to 8, and second equation is really 2Y1 plus Y2, that's equal to 22. So simple forward substitution will do the job. So Y1 is already given to us. Y2, you do just substitute this thing here and get me a Y2. So what's a Y2 here? 6. So that was painless. Then we say, okay, this is the vector Y that I want is this guy. Next, I go to the next stage. This is okay, upper triangular matrix U, this matrix, times the original unknown X is creating this intermediate Y. So I say 2 minus 1 minus 3. Okay? So we are trying to do this one. U, here's the U. X, I'm trying to find, so I'm going to call it X1 and X2. Capital X is a bunch of little x's. Here are my little x's. Y, who's my Y? What I just found on the previous stage. Sorry, I probably couldn't see that. Okay, 8 and 6. Okay, so once again, this is my U, this is my X, this is the Y from the previous stage. Well, how do we solve this? This one also we said is painless. If you want to rewrite it in the traditional format, and What is the style of solution here? We called it back substitution. So this is a back substitution style. This one, in comparison to this, is called forward substitution. So you start from bottom, solve that one. So what's my x2? x2 is negative 2. I take it, put it here, negative 2. So I have 2x1, negative 2 makes it positive 2. Take it to the other side, 6. So x1 comes out to be 3. So here's our final solution. Okay, once again, let me emphasize, just for sake of clarity, so that in the next test there wouldn't be any kind of objections. How come I didn't get any points? Real question isn't really getting X. Real question is understanding the role of permutation and applying the LU factorization to get it. So this was a crucial component here. We never went ahead and figured out what A is. We didn't deal with the matrix directly. Presumably it was there originally. Somebody factored it, did everything. This is like in a recycled stage of using all that information, as opposed to very first round. So you make sure you practice some of the problems on that page. Examples from the section 1.5 that matches this type of approach is problem, say, 33 through 36. Other applications are also mentioned, but since we are falling behind, let's just go ahead. We are going to enter section 1.6, and that is a section where a lot of stuff is kind of pushed in it, kind of not related. Yes, question.
So our X and Y columns, it's always just going to be like one column? Is there going to be like maybe like two columns?
All of these problems that you are going to face here, they are all just vector, one single column. Yes, these are all of them a vector of unknown quantities. You are not going to see a matrix. Any other question? Okay, as I was saying, in section 1.6, a lot of stuff are pushed in it. It's kind of whatever that didn't fit anywhere else just was thrown into that section. So we have the concept of symmetry, concept of transpose, and some other items that I'm going to bypass now due to shortage of time. The band matrices are mentioned, applications of linear algebra to issues such as statics, course that you take in engineering, that's also mentioned. Let's just keep it simple. So that is what we are going to talk about. In some applications, matrices that you end up with have a special look. One of the special looks that are investigated are symmetric matrices. Symmetric matrices simply means that if you have this square matrix, first of all, it has to be square. Second, you take its diagonal. That diagonal acts like a mirror, meaning if you have some quantity here, exact same quantity shows up across this diagonal in a position whose rows and columns are columns and rows of this one. Similarly, if you have some other entity here, the entry that is symmetrically positioned with respect to this mirror on the other side occupies exactly the same number. Let's just give some examples. Here is a simple one. Suppose I have 3, 5. If this entry is 7, what should be the entry here to make it a symmetric matrix? 7. So what we want is that across, this is the main diagonal. This is an entry that is seated at the position which is row 1, column 2. This is a row, this is a column. This one is the entry that is seated at the location which is row 2, column 1. This is a row, this is a column. The two entries have to be the same. Let's try it one more round. Suppose I take a bigger matrix. This time I have 1, 0, 9, say 8. If this entry is 11, what other entry will be 11? Call it by its row and column number. 2, 1 has to be. If this entry is, say, 35, which other entry will be 35? Again, call it by row and column number. Let me see. Let me make it clear. Okay, so this is row 4, column 2. Going to the other side, I will go to row 2, column 4. So it's going to be 35 seated here. And so on. If I have an entry, say 10, who's going to be 10? 4, etc. So if I have a matrix, A, which has entries, we said we call this A11, A12, and going down the road all the way to A1n, and then going down A21, A all the way to N1, and then finally ANN. We say A is symmetric if and only if the item that is seated at the location ij is exactly the same as the item that is seated at the location AJI. Okay, for example, if this is my matrix A, this one is going to be A41, which is 10. This is A14, which is 10. For the matrix to be symmetric, these have to match for all entries. All entries means 1 through n. Well, there is another kind of special look that shows up in application, and that's called skew-symmeric. That is defined by a kind of matrix whose entry on location ij is simply negative of its entry on location ji. So across from the mirror, the two numbers are the same except for the sign. That also has a lot of application. Let's start by a simple case. Suppose I have just 2 by 2 matrix. If this entry is 5, what other entry of this skew-symmeric matrix do we know about? The entry at the location 2, 1, and what is that going to be? Negative 5. Now, what kind of a number can be on this diagonal if this is supposed to be applicable to all I and j's? For example, can I put, say, something like 7 here? What is the address of this? The address of this is A11. This is saying if I flip the row and column, I have to get something that is negative of this. Well, if I flip the row and column, I'm still looking at A11. But if A11 wanted to be 7, after I flip the indices, I have to get -7. So I cannot put a number like 7 here because it doesn't match this description. This description says for all I and j's, this has to be true. So, for example, if I and j's were the same, and I'm still insisting that this number has to be negative of itself, there's only one number will be left that fit this description, is 0. So we understand a big thing, that on a skew-symmetric matrices, the main diagonal is made out of just 0 entries. So all 0 on main diagonal. Now, one of the exercises in this section, we have a general simple theorem that says if you got any arbitrary matrix, you can always break it up into one symmetric and one skew-symmetric, sometimes called anti-symmetric matrix. Here's the idea, kind of a big idea, so sometimes called a theorem. Big ideas are called theorems. And this is every matrix, means anything, any arbitrary matrix. We still, of course, we are insisting on compatibility, so of course it has to be square matrix. Every square matrix is sum of a symmetric and a skew-symmetric matrix. Here's an example. Suppose I give you some matrix. Suppose it's 5, 11, 9, say 17. Write A as sum of B and C, where B is symmetric, C is skew-symmetric. That is this connects to, say, problem 19. Okay, I want to write it as sum of B and C. B is supposed to be symmetric. Let me write it B11, B12, B21, B22. I don't know what's going to be in it, so for time being, I just keep space for myself. Now let's clean the clutter and try to reduce these things. So these B's indicate this capital B matrix. The C's indicate entries of this capital C matrix. We are insisting that this B has to be symmetric. So what is true about these two entries? They have to be the same. So let me just call that so B11, B22, those things we don't know. And let me just call this guy B for short, for time being, so that things don't. Okay, what do I know about the entries here? I know a little bit more. What? Yes, very good. So these entries got to be 0. So this is 0, this is 0. Yeah, very good. So this is going to be negative C. Is that right? So whatever 5, 11, 17, 9 are going to be broken down to, those matrices have to have such looks. Let me see. You can just kind of guess who's going to be left for B11 anyway. It's just 1, because B11 plus 0 has to match 5. So this has to be my 5 here. And similarly, B22 is going to become 9. Is that right? So the entries on the diagonal are inherited by the symmetric matrix. On the skew-symmetric matrix, these guys have to be just zeros. Now, how about the rest of the stuff? I'm left with figuring out who should be B and who should be C. I can get some very simple recipes for handling that. What can I say about B and C? B plus C has to add up to 11, and B minus C has to become 17. So this is actually becomes a simple system of equation to solve. You don't need to go through Gaussian elimination to do that. It's just very, very basic. So sum of two numbers is 11. Difference of them is 17. However you do it, what is B? Well, let's just do it some way. You add them up. You add these two up, so it becomes 2B is equal to 11 plus 17. So B is 11 plus 17 over 2, which is what? So this entry is the average of this and its sister entry. Okay, so on the diagonal, on the symmetric matrix, on the diagonal, you're just copying the original diagonal. On the off diagonal, every entry turns out to be average of the corresponding entry and its symmetric location over there, like 11 and 17 gives you average of 14. This is going to be 14. How about C? Well, you have to subtract these two. You say C is 11, so I subtract these two equations. It's 11 minus 17. So C is going to be 11 minus 17 over 2, and that is minus 6 over 2 is minus 3. So every entry on the skew-symmetric matrix is equal to the original minus its sister location entry divided by 2. So I take 11 minus 17 divided by 2, I make a minus 3. How about this one? I have to do the entry minus its sister location divided by 2. So what am I going to get? Just opposite of that, which is going to be 3. So the recipe for breaking it down is pretty straightforward, and you can have a simple question like that on the test, or something a little bit more substantial. Okay, so we talked about symmetric matrices and skew-symmetric matrices. That brings us to idea of, well, we are looking at the matrix, looking at some entry here, and looking at symmetrically positioned entry there. We can physically turn our matrix around and just exchange these entries. That turning of the entries of a matrix is referred to as a transpose. Transpose of a matrix is defined for any size matrix. It doesn't have to be a square. So just to make it clear, let's pick up a matrix with these entries, say A, B, C, D, E, F, G, H. I'll call this matrix A. Transpose of A is shown by, depending on what book you use. Typically they use letter T. So let me write it here maybe. So, transpose of A, which is shown by A with a T on top of it. Sometimes they put an apostrophe or something. Just the same thing, except that the rows have been turned into columns and columns into rows. So it's A, B, C, D, and then E, F, G, and H. Okay? Now, suppose I have a matrix that to begin with is actually square, A, B, C, D. What's the transpose of it? First of all, that's going to be also square, so same size. What are the entries of it? A, C, B, D. If A is symmetric, what happens? If A is symmetric, this B is same as this C. Is that right? Which means this B is going to be same as this C, and this C is same as this B. So if A is symmetric, what happens is that if you turn it around, you end up with what you got. Like if I had 5, 3, 3, 7, I can go ahead, exchange rows and columns, but after I do that, I end up with whatever I had. If this 3 comes down here and this 3 goes up there, Well, nothing changes really. So symmetric matrices have the property that they are equal to their own transpose. What do you think happens to a matrix that is skew-symmetric? Like suppose, give me an example of a skew-symmetric matrix. We said on the diagonals we better have zeros, and then 7 minus 7. So suppose this is my matrix. If I transpose it, what do I get? What is the entry here? 7 and minus 7 and 0. Now, if I compare these two matrices, what can I say? What's the connection between the two matrices? Are they the same? Obviously not. This is 7, this is minus 7. But there is still a simple connection between these two. What's the connection? If you take a skew-symmetric matrix, transpose it, you end up with a matrix that is a negative of the original. Okay? So symmetric matrix A is equal to A transpose. Skew-symmetric matrix B is equal to negative of B transpose. You can write this thing also to say B transpose is same as minus B. Same thing. So you can cook up a formula using this notation for figuring out how to break up a matrix into a symmetric matrix and a skew-symmetric matrix. Okay, there is a section on banded matrices and sparse matrices, but that really requires a lot more practice than what we have gone through, so I'm going to skip that and start. We are bypassing the section on determinants. Because the full section is kind of lengthy, it has a lot of stuff in it. Every now and then we still need to do calculation of determinants for some small matrices. We will come back to this issue when we need it. Let me just mention, just in case you go to some other courses, either in math or engineering, you might need to have information at least about the determinant of a 2 by 2 matrix. Let me see, those of you might remember this thing from high school or some other class. What's the determinant of a 2 by 2 matrix? It's a quantity that plays a significant role in, it's kind of a signature of a system. Tells us a lot. Let me just, for the sake of completeness, also mention 3 by 3. So the determinant of a matrix is a number. That number tells us a lot of stuff about the matrix. It gets to be used in many, many formats. It's just that determinants tend to be a very messy objects. Well, you have seen a lot of mess, but this is a bigger mess than anything else you have seen so far. So sometimes people avoid them on the first reading. But 2 by 2 and 3 by 3 are still not that bad. Let me see if anybody have seen how to handle 3 by 3 matrices, some way of memorizing what that entry is. So it's a long list of things. You see that it takes a while to say it. Here is the easiest way to kind of to rattle off all the entries. Easiest way is just to copy your matrix again. Sometimes you don't copy the last column. And then on this, go ahead, look at the main diagonal and this one and this one. Multiply all of them by +1. So you are going to have AEI and then BFG and then CDH. And then go the other way, AFH, this time multiply by minus BDI, and then CEG. Notice the CEG is same as CEG you see here, so your teacher might have not insisted on writing this one. Let me put a big warning here. How do I put a big warning? This kind of gimmick is only good for 3 by 3 matrices. No such thing for 4 by 4 or 5 by 5. That's why it needs a whole chapter, a lengthy chapter. Like here you see 6 items. Guess how many items you are going to see? Like here you see 2. Here you see 6. How many do you think you are going to see when you are dealing with 4 by 4? Let me see if you can. But if you have just one number, determinant of that number is just that number. So for 1 you get 1. For 2 you get 2. For 3 you get 6. The question is for 4, what are you going to get? What does this sequence remind you of? 1, 2, 6. Next guy is not 8. No. What is the pattern here? Let's imagine one of those questions you used to have in high school. What's the pattern that is you see in the sequence? Very good. So how do you get 24? This is twice this is 3 times that, this is 4 times this one, and next one is going to be what? 120. So imagine having 120 things written here, so whole page again going to get filled up. So obviously there is no such hope, no simplistic step like this. Just draw a bunch of lines and get 120 things out of it. That's not going to happen. So again, only a way of memorizing really doesn't have any significance to it. So if you come across them, you know what to do. And when we need them, that's how we are going to calculate them. But for now, we are going to go to chapter 3, which is a chapter on vectors. Okay, first let's mention some applications so that they don't look very mysterious or abstract objects to you. And then we come to mathematical representation. What are things in nature that you study in other courses which are referred to as vectors? What kind of things are vectors? Velocity. Okay, so velocity, like on the afternoon news when they are showing wind pattern and the air, the weatherman is just talking on and on, like I talk on and on, and you're not paying attention and just wanting, is it raining tomorrow or not? That's all I want. And it takes 15 minutes to tell you if it is raining or not. But every now and then you see the map of United States there, and they put a bunch of arrows on it. Okay, so that is referred to as a velocity field. Each of these things is a velocity vector. Velocity vector, when the weatherman wants to talk about wind, it says maybe it's 20 miles an hour and say in the northeasterly direction. It gives you a direction as well as a magnitude. So velocity has 2 things. It has a magnitude and it has a direction. Or instead of magnitude, you might call it a size or something like that. So velocity is wind velocity or velocity of anything has these 2 components, a direction and a magnitude. What other quantity do you know that is typically referred to as a vector? Say? Electric field, yes. Electric fields are made out of electrons moving in a certain direction. So first you want to know how fast the electrons are moving, and second you want to know in which direction they are moving. So just like velocity of anything, the velocity of water, velocity of air, you can have velocity of electrons. So electric current is really a vector. Anything else? Yeah, magnetic field, so magnetic flux. So we have magnetic field or electric field. So those are examples of actually vector fields. But similar to them, you have gravitational field. These are really examples of vector fields. So how does that work if you have Earth? Well, if you are here, you feel some force is pulling you down. Well, let's draw this bigger. So, okay. If you go into space, that force becomes less. So the force, which is indication of the gravitational field you have, is having some magnitude. Now, if you move over somewhere else, the direction also changes. So if you are on the other side of the globe, the force that is acting on you is the opposite of what it is on this side. So gravitational field, and similar to that, magnetic field and electric fields are made out of a bunch of vectors. So the idea of a field simply means you got a lot of them. That's all. And these are all examples of forces. So really, the word that I was looking for, velocity is a vector, so is force, and force is also connected to acceleration. And examples of velocity, of course, we have electric current, water velocity or air velocity, or velocity of any object. Okay, now vectors act in a way that is kind of different from ordinary numbers. Suppose you are standing here and one friend of you is pulling you in this direction and another friend of you pulling in this direction. What happens to you? Might express some pain, or it's just you are not going to move anywhere. So the sum of these two vectors is going to be a zero vector. So zero vector in that case is referred to as a resultant of these two. Now if these two friends pull you in these two directions, in which direction would you actually move? So somebody is moving, pulling you to east, another person is pulling you to north. Or just imagine, if getting out of a social situation, suppose there is an object here and you are putting two forces on it. What would be the resultant movement of this object? It's gonna move in this direction, and the force that acts on it is gonna be equal to length of this red curve that we have drawn. So this is referred to as a resultant. Resultant force is a single force that does the job of everything else that was being imposed on the system. So if you have an object and there are a variety of forces acting on it, for a certain situation, all of these forces can be replaced just with one that does the job that is equivalent to all four of these things that you see here. So that's going to be referred to as a resultant force. Now, how do we handle vectors mathematically? That is what we are going to pick up next time and talk about it. So what you want to do is to finish section 1.6 and problems of 1.7. Start reading 3.1. And I'm going to see you on Friday.